is ready. Yes, Giovanni Amelino-Camelia, please.
There it is. Okay, so thank you for having me, and I'll try to give the perspective of a quantum gravity theorist on this generation of telescopes, and in particular, thinking of Hermes as an opportunity for quantum gravity. I will also use this opportunity to balance. There is, and it is a beautiful success of these last few years that quantum gravity theorists and astrophysicists have been talking to each other, and there are some messages from research in quantum gravity which have been really embraced by astrophysicists worldwide. I am now geared toward a second stage of this, where this communication becomes even more effective. And so I will aim to render the message from the quantum gravity side a little bit more articulated than it has appeared so far to many, understandably, to many in the astrophysics community. The one message which was effectively metabolized by the astrophysics community is that we have found out over now more than 20 years that in some of the models, not all, I should stress, but there is a zoo of models in quantum gravity. Quantum gravity is not one thing, it's very many things. Like in all areas of research, when research is starved for data, theories abound, unfortunately. And so there is a zoo of theories, but in a significant fraction of this zoo, we are finding, and interestingly, with the different mechanisms at the source of it, we are finding that the shellness condition is modified by the quantum gravity scale, which we assume to be close to the Planck scale. The first results of this sort were understood as a manifestation of a breakdown of relativistic symmetries in these theories. And a posteriori, this is correct in a subset of the theories which provide this evidence of modified on-shellness. But then gradually we understood that this was also in some other significant fraction of the models, not a breakdown of relativistic theories, but just a deformation of relativistic theories, which you can easily imagine intuitively if you think of the transition from Galilean relativity to Einstein's special relativity. One should probably see special relativity as a deformation of Galilean relativity by a dimension full scale, the speed of light. And in the same mathematical sense, this class of relativistic theories which we are studying is a deformation of the relativity of Einstein by a dimension full scale, which is the quantum gravity scale we assume to be close to the Planck scale. And the code words for these two possibilities are LIV, Lorentz invariance violation. This is stuck in the community as the good acronym for it. And DSR, doubly special or deformed special relativity for the second possibility. I have a feeling that the first possibility was well metabolized by astrophysicists, but the second is still not fully appreciated. And this is not so important. I mean, the theorist concerns are not so important for observations, but as I'll try to stress, there are also differences in the way these two mechanisms manifest themselves in data. Even if when they share something like a modified on-shellness, there are differences that observers should be informed of and equipped with in their studies. And as a theorist, the most exciting recent development in this area is that we are appreciating that a common feature of most of the theories in this case that support these effects is that their momentum space is curved. Now, this may seem strange, but we have growing evidence that this is the case, and we are starting to understand that it makes sense for a quantum gravity to have a curved momentum space. And actually, of course, we want to do 4D quantum gravity, and that's too hard for us still. But for many decades, it was also too hard for us to do 3D quantum gravity, the dimensionally reduced case. But over the last decade or so, 3D quantum gravity has been nearly fully understood. Several technical hurdles were handled. And actually, 3D quantum gravity is a theory of this DSR sort. I mean, gravity is purely topological in 3D, so it's easier to deal with its challenges. And the topological degrees of freedom of gravity can be integrated out. And what you're left with is that gravity is, not gravity does this, gravity is in 3 dimensions, 2 + 1 dimensions, gravity is curvature of momentum space, quantum gravity. And this curvature of momentum space produces a modified on-shellness and produces a DSR type modification, deformation of relativistic symmetries. So for example, this effect that many also on the astrophysics side have considered, this effect of an energy dependence of the speed of ultrarelativistic particles, such as photons and typically neutrinos. These modifications of the velocity, they actually are, and that will require another entire presentation to explain, but this is dual redshift. We now understand in completely geometrical terms as the dual to redshift. So it's the dual curvature or momentum space that causes this energy dependence of the speeds. And it is a very small effect. I'm here showing all expansions in powers of the ratio between the energy of the particle and the Planck scale. And this ratio, of course, for all the particles we managed to observe is extremely small. So on terrestrial scales, there is no chance to see it. It might have been there in all the laboratory in the history of mankind, and we would never notice. But at some point, we realized that astrophysics, so I like to say, using the universe as a laboratory was big enough. And in particular, gamma ray bursts, on which many of the presentations have focused, are a particularly striking opportunity to test this very small effect. This part of the message also has been metabolized by many astrophysicists, and I think is a huge success. Like on the other side, I am learning a lot of astrophysics, which is good for your health anyway. It's like eating fruits and vegetables. And one point which has not come across from between the communities is that all these results that I'm mentioning with such confidence, because at this point they're very robust, actually much more robust than when I started to give presentations in meetings such as this. Now they're very robust, but they are still for flat space-time. So in the modern language, recent language, is theories with curved momentum space and flat space-time. Of course, as you realize that you need the universe as a laboratory, the universe is not flat, not even in first approximation. The curvature of the universe is appreciated in all our data and affects the time of flight of particles. So we need results. In the modern language, we need results with both curvature of momentum space and curved space-time. And these are very hard. I mean, this is now a blooming area of theoretical research, but we are dealing with a number of technical and conceptual challenges. We are making progress. I think actually the last 2 or 3 years have been particularly significant in this sense, but still we actually are coming up with another zoo. So we have now a zoo of possible redshift dependence of the effect. In flat space-time, there is a dependence on the time of flight, which is now very well understood. In a curved wave space-time, we need a dependence on redshift, basically. In FRW space-time, we need a dependence on redshift of this effect. And we are coming up in different theories as we manage to break through and finalize computations. We get different formulas for the redshift dependence of the effect. In some cases, but only in some, actually the results we are finding reproduce a heuristic argument made more than a decade ago by Jacob and Piran, which set the standard for the current phenomenological studies. The redshift dependence is the one in this formula I'm here showing, which is assumed in nearly all phenomenological and data analysis. This formula actually, to me, is even surprising that it does, but it does match the result in some models, but it's not all we have. And we have, with equal standing, with equal apparent likelihood, other forms of redshift dependence that need to be studied. And there are significant differences, especially for the way the effect starts to grow at small redshift, and then how it ends up taking speed, let's say, to getting bigger as redshift becomes significantly bigger than 1. So there is growing interest from quantum gravities like me in a plan of astrophysical studies which improves in particular our ability to observe very distant sources. Between the different formulas, alternative to this one that we are studying, having information on very high redshift would be magnificent. So since I don't know how much of the rest I'll be able to go through, let me have this slide to summarize what I see as the most important opportunities that Hermes will provide to quantum gravity research. To begin with, with a big collection of mini satellites, there could be very high statistics. My reference is Fermi. I am imagining Hermes with the full deployment of mini satellites to provide higher statistics, but at lower energies. Lower energy is not good for quantum gravity, but higher statistics is very good, and also the better timing that Hermes planning is aiming for would be evidently, from what I'm saying, an important resource. I'm also hoping that something like Hermes could allow to have more observations of GRBs at large redshift, which I just mentioned being at this stage one of the hot topics for those involved in this quantum gravity research. We need to test the differences between different formulas for redshift dependence, and the large redshift realm is crucial. Something I will not take time to explain also is a very recent result and very complicated relativistically, but also, and this is not only for Hermes, but perhaps Hermes can also be very significant in helping for this. We would need to understand better the bulk gamma factor of these sources, possibly in the ideal of a theorist, also getting reliably bulk gamma factor for different phases of the burst evolution. What we are also finding in some of the recent studies that the boost of the source, let's say, with respect to us, how much the source is boosted toward us, actually affects our formulas. So the formulas I'm showing are actually still the old formulas, assuming no boost. We did calculations assuming relative rest between telescope and source, which of course, especially in the case of gamma ray burst, is not the case. We have this signal which is strongly boosted toward us. And but actually, and this is something that I discussed in the early days of thinking of Hermes with, particularly with Fabrizio and Luciano, is dual lensing. So the other side of the current momentum space story instead of being effects in the space-time, one space, one time direction plane of propagation of the particle, in equally significant instances, we have similar effects in the plane orthogonal to propagation. And this is a geometric effect which we call dual lensing. And this would mean that the way we see a source, the direction that a source appears to be seen by our telescopes, is actually energy dependent. Is an artifact, is a relativistic artifact. The source is somewhere, of course, and where it is, we could say, is where low energy photons tells us it is. But we are predicting that the position of the source in the sky should move as you grow up in energy. So there is huge interest right now in very good localization of these sources. And what is exciting to me, well, and frustrating at the same time, is that this would be totally new game, because I have tried to play with numbers, and right now dual lensing is totally unconstrained, basically. The effect is also very small, so we would need to start studying it, achieving the best localization of sources in the sky as possible. This is my list of desiderata for and motivation for Hermes. Let me go back, however, and this is mostly, as you see, is mostly new, opening new ways. This is the most exciting part of Hermes, opening new directions in this phenomenology for quantum gravity. Let me now go back to what we have been doing so far, which is basically testing the Jacob-Piran heuristic but powerful ansatz for the redshift dependence of dual redshift effects, as we should now understand them. And just to show you that there is an intriguing point that I should submit to astrophysicists, which from the astrophysics side is intriguing to me, in analyzing this formula using only the photons of highest energy seen from GRBs. Here redefining, I'm introducing this E star, which allows me to study the Jacob-Piran formula as a linear relationship between the times of arrival and an effective redshift and energy dependent quantity E star. So I'm testing a linear relationship which shows better on graphs. And what is interesting is that if I, and this is started with work within the group of Bokyang Ma in China, and later we helped establish with more powerful techniques the statistical relevance of this feature. If you focus on the most energetic photons seen by Fermi. So in this graph, I have not signal from one GRB. These are 11 points, I think, and they are from 7 or 8 GRBs. Some of them contribute a couple of points, because we have this cut on energies of the photons that must be of energy greater than 40 GeV at the source. And we just plot this E star, which I defined on the previous slide, versus the delta T, intended as the time of arrival of the photon with respect to the peak of the GBM in Fermi, first peak. It's just interesting that there is a pretty high correlation overall in this data. And you can test this. It doesn't look, they're not on a straight line, of course, but the amount of correlation that this graph shows is statistically rather intriguing. I mean, if you imagine, if the hypotheses of the test were incorrect, you would expect these points to be rather scattered in my box, and instead they line up roughly. And you can just calculate the correlation on this graph and see that its value is rather unlikely to come up accidentally. However, I have circled one point. So this graph would get me very excited, or at least excited, because the statistical significance should get even higher to get me very excited. But it would get me more excited if not for this point, which I circled in red. This point you see is below, probably doesn't appreciate the way I'm plotting the graph, but is significantly below this line that other points suggest, and is significantly below, and it is a point from GRB 090510, this photon with about 30 GeV, and to make it simply, in order to make this one point become acceptable in relation to the inference that one is making by studying this correlation in this graph, I should actually argue that it's just an accident that these, I'm here showing only points from GRB, and this is just time versus energy, time after trigger versus energy. And I'm just showing photons with energy more than 1 GeV from GRB 090510. And you see that this 30 GeV photon came just at the time when the signal was busiest in the range of a couple of GeVs. And in order to, so this would mean, if I take it in the way that seems natural to take it, this would mean that if there is a time of travel difference between photons of a few GeVs with respect to 1 or 30 GeVs, it has to be very small. It has to be such that that group of photons in the bottom part of the graph still arrives roughly at the same time as our 30 GeV photon. So this on its own would appear to support that the effect is very small. And actually, interestingly, it supports a value of the quantum gravity scale, which is at least not much bigger than the Planck scale. At least not much smaller than the Planck scale, not much bigger than the Planck length. And which instead, the correlation found in this graph would suggest actually a bigger quantum gravity length scale, so a lower quantum gravity energy scale. And so, well, I wonder, I mean, this is the status of some of my considerations and considerations by the Rayton group. So I'm submitting in case you have ideas on it. And now I quickly close. This is a living review. Quantum gravity phenomenology is a big field of which astrophysicists have graciously embraced a part, but you might be interested in learning that is a much bigger field. There are very many areas of phenomenology which are influenced. One spot in closing is that the Planck scale is really a first guess. I don't have time, but actually we are extrapolating the value of the quantum gravity scale from low energy data. And if you think of how renormalization works, of how coupling constant running works, you actually should expect that we get it wrong. So in our papers, we should never write the Planck scale with too many digits. I haven't read the many digits that sometimes are in some papers. And finally, in another effect, which in astrophysics has been taken under consideration, is the one of threshold anomalies. For example, the absorption of 10, 20 TeV photons by the far infrared background could be suppressed by these same quantum gravity effects. And this is a very interesting opportunity also because the study of the opacity of the universe is, as I understand it, an improving area of astrophysics. I should stress that this effect is allowed in Liv scenario when you break relativity, but instead is not there when you deform symmetries. It's just a symmetry principle that you cannot have threshold anomalies. And I stop here since I think I'm out of time.
You are perfectly on time. Thank you. So questions for Giovanni?